Well, hello. My name is Ioan Constantin. I'm from born in Romania. I think it's my third time here at DefCamp, but my first time on stage, so I might get a bit nervous. Maybe my jokes won't appear as funny as they should be. But now that I have my pointer, I'm going to hopefully not bore you for the next 45 minutes, talking about advanced persistent threats, complex threats, and machine learning. I'm going to do my best not to pronounce the words artificial and intelligence in the same phrase. And during the next 45 minutes, I'm going to answer 3 important questions, the real questions. The first one, which James Bond movie is the best? The second one, how long does it take for mankind to get from Earth to Mars? Just a one-way trip. And the third question is a bit technical, we're gonna get there. All joking aside, my presentation starts with the big question. How do you go about finding a needle in the haystack? This is actually a funny quote from a superhero movie, and the answer is pretty basic. You bring a magnet. And what are our haystacks? Huge amount of data. This is our current haystack. We are generating large amounts of data. We are generating large metrics, logs, bits, and stuff like that. We are trying to process them. We are trying to find threats that might be dormant, hidden somewhere in that huge data set. And we are kind of having a hard time doing this. On today's agenda, I'm going to go through what are complex threats. I'm not going to stress this point necessarily. I'm assuming that most of you guys are already familiar with APTs. I'm going to talk about context and the post-hash context, the post-signature context. What do our machines, our technology need to go beyond detecting threats, detecting signature events? And of course, one answer might be machine learning. I'm going to give you a sneak peek, just a sneak peek, a very high level overview at what we're doing back at Orange in using some advanced algorithms to detect some very advanced threats. And hopefully, maybe next year at that DefCamp 10, I'm going to also present you a demo. And of course, I'm going to answer that last question I was saving for the final slide. Are we trying to replace our CMs? Are we trying to build another open source CM? Well, spoiler, no, we're not. So let's go ahead with complex threats, advanced and complex threats. You all know them. You all heard about them. They use sophisticated 0 days. They use cloaking and stealthy mechanism to gain a foothold, a stronghold in your network, and to spread, to move laterally. They are persistent, as the name implies. They do a low and slow approach to attacks. They gather ground, they gather information, they move laterally, they exfiltrate data. Sometimes they even break things, as in some recent cases with VPN filter and such. And very important, they are task-specific rather than opportunistic. Keep in mind that these threats are designed from the get-go, from the ground zero, from the 0 point to be as complex to detect and as complex to operate as they can be. They are not your simple, your average malware that, one antivirus, anti-malware solution just opens up a beacon like a red bulb somewhere, hey, you got a virus. No, these are threats, these are complex software that are built with, in some cases, they are backed by state nations, by intelligence agencies, by companies which can, put forward a huge effort in designing software. And they are highly dependent on social engineering, on surveillance, on supply chain compromise. What can we do to at least have a chance in detecting this kind of threats other than, building a huge wall of IPSs and firewalls and things like that? Well, in order to detect an APT, you got to know what are the stages of the inner workings. And this worm thingy here, which reminds me of the game Snake on the Nokia, all Nokia phones, it's actually self-explanatory. You have 6 or maybe 7 stages that one such advanced threat may use in order to complete their mission. And you have your initial compromise using either social media or phishing emails, which is very common, or in some cases infected storage devices. You have your foothold establishment, you know, where the malware, the software, creates a controllable tunnel, stealthy tunnel, to a control server, to a C2 server. You have some form of reconnaissance. The thing looks around, finds other vulnerable systems, you know, just maps out the surroundings, and then it moves laterally. And this is the really bad thing it does. You know, it uses privilege escalation. It uses some form of exploits. In some cases, 0 days exploits, things that cannot be detected as easily with traditional methods. It does keep a low profile. We're going to see in a couple of slides that in some cases, you have APTs that are laying dormant for years on end in networks, like very high-profile cases, or they keep doing the bad thing that they are supposed to do for 2 or 3 years. And in final, they complete their mission. They exfiltrate data, they break stuff, and sometimes they do keep a backdoor open. Maybe they want to, you know, return to the scene of the crime. According to a Trend Micro survey, which was, if I remember correctly, based on maybe 2,000 or something answers from small, medium, and large companies alike, these are some of the technical controls that most companies are using to protect against APTs, specifically. I entered this slide here in my presentation just to give you an overview on the wide spectrum of technical measures that companies are trying to use in order to prevent such infections, such threats. Nobody knows for sure what to do. Nobody has a catch-all answer, like, you know, you should use this solution, this technology from this vendor, or you should use this method in order to be safe, or at least be at a reasonable level of safety against such complex threats. Some are using antivirus and anti-malware specifically to protect against APTs. Others are looking at their mobile endpoints with mobile device management and mobile security gateways. And some of them, most of them actually, are relying on the traditional, you know, borderware enforced firewalls, new generation firewalls, IPSs, IDSs, hoping that maybe they could catch a break if, you know, somebody tries to sneak in their networks. And 64% of them are trying to use some form of log correlation, log aggregation, or CM tool to detect something more than just your average run-of-the-mill malware. There's challenges in mitigation, and this is probably the main reason that people are kind of holding back on investing in cutting-edge solutions, because they're possibly waiting for the playfield to level. You have your malware variety. There are literally hundreds of millions of malware species and malware variations that were actually let loose in the wild just back in 2017. That's hundreds of millions. You know, you have traditional security that can be ineffective in these cases. You don't necessarily have to or expect to rely on your firewall to detect something that was cooked up in a Chinese laboratory just 2 weeks ago using a 0-day that was snatched from a, I don't know, network chipset producer back in Taiwan. You simply cannot rely on your firewall for that. And log analysis and log correlation has its limits, because if you don't provide enough context to log files or to log data, well, log data remains just that. A huge index, a huge database of events that you can browse to, and maybe you can build a couple of correlations back and forward, but you don't get the big picture. You're not seeing the trail. Maybe you're just seeing the breadcrumbs. And there's, of course, a lot of noise. It's extremely hard to separate legitimate traffic from bad traffic in our complex, large networks nowadays. You are a telecommunications operator. We are, if I'm not mistaken, we are boasting maybe 11 million customers. You can imagine the level, the sheer volume of traffic that we might want to inspect for malware, for threats, using traditional security. That is simply not going to work. And this gets us to my first question, if I'm not mistaken. How long does it take for men to fly from Earth to Mars? It's 160 to 180 days. And that's exactly how much it takes for an average company to detect an APT. Maybe you can go back and look at your activity for the past 6 months. Things you work at your job, documents you redacted, you created, code you written, and think that somewhere in your network there's this thing staying there like lying dormant that exfiltrated every bit of information that you created on your workstation, on your file servers, and you simply don't even have a clue that this is happening, because it takes up to 39 days to mitigate such threats, and 43 days to recover, to remediate. This is bad. I know it looks bad because it is bad. And this is just a statistic done by the Ponemon Institute for the first 6 months of 2018. And there you have it, your obligatory timeline slide, and this answers to my first question, or actually my second question about the James Bond movie. I know most of you are familiar with this. Most of you have seen this. Some of you have even worked with this. You have your Moonlight Maze, the first APT that I, for one, know about. You have some guys in Russia breaks into system from Pentagon and NASA and the US Department of Defense, and they exfiltrate thousands of documents for nearly 2 years in a row. Then you have Titan Rain with various Chinese sources attacking some large defense contractors, the people that build rockets and stuff. And you have your GhostNet, your Stuxnet, with the Iranians and the nukes. Your RSA attack, where, Adobe Flash and phishing email equals love. And then in 2018, you have your garden variety VPN filter, the thing that actually infects your router, and God knows what it can do with it because it's modular. You can update it on the fly if you control it. What this slide and what this timeline is about, well, it's about the best spy movie that I've ever seen. You got everything from Chinese hackers and Russian hackers breaking into the Pentagon. You have nukes, and you have state-of-the-art technology and malware. There you have it, APTs. So, solutions. You can go about and do pretty much everything, and you should do everything in the, left side of the slide. You can do proactive security, you can do bug bounty programs, you can do threat hunting, and I encourage it. You can do, of course, threat intelligence with open source intelligence, human intelligence, and social media intelligence. But the thing that you gotta take from these activities is that you gotta provide context. You have to provide context to your machines, to your traditional security, in order to detect a stealthy presence. So maybe machine learning is the solution. I don't know. We'll see. Stanford University and the University of Washington have 2 definitions for machine learning. I personally like them because they are kind of complete. They run full circle. Stanford University says that machine learning is the science of getting computers to act without being explicitly programmed, while the University of Washington says that machine learning are algorithms that can figure out how to perform important tasks by generalizing from examples. This is the two definitions, and this is the two strong points that we are building our platform that we are going to preview in a sneak peek in the several future slides. What does machine learning for cybersecurity? What does it do? What is it good for? Well, it allows you to learn from available data by using representation, evaluation, and optimization. You know, it allows you to train your machines to act by creating a baseline and observing in time, in a timeline, how specific input go above or below that baseline. It allows you to find anomalies. And by identifying anomalies, you actually stand a chance of finding stealthy, hidden things in your networks, in your data, in your information. And of course, if you want to go the full route, go full Skynet, Robocop, you can let it act upon finding. You can automate your detection and mitigation. What is the available data that you can work with, and we are actually working with in our test machine learning, cybersecurity, threat detection, threat intelligence platform? Well, you have an active network equipment, noisy things, you know, like routers, switches, printers, everything, APs, AP controllers. They all generate tons of data. You have your endpoints, you have your fixed endpoints, you have your laptops, you have your mobile devices. You can get metrics like OS logs, hardware logs, security logs, and everything in between. And you have your applications. You have your applications that can run both client and server. You have your email clients, you have your web browsers, your VPN clients. They come in all shapes and sizes. They run on anything from MS Windows to iOS. They all generate information, they all generate logs, they all can tell you something about what's going on inside them. You have your security products, and you have some other, you might just have some other cool stuff in your networks, as we do. Because we are a large telco, and we generate huge amount of data from very specific, very business-specific equipment. And this brings us to our sneak peek, which is going to be very brief and very high level, at this platform that we are currently developing, which leverages every data source that I've mentioned in the previous slide, and adds something to the mix. We can add our info regarding cellular data. Don't worry, this is highly anonymized. We really don't need to know which of your cell phones did what and who are you, but we need to, we are maybe interested in finding out and figuring out some trends. You have your Wi-Fi data, because we operate a large Wi-Fi network, both for consumers and business customers. We have some security data that we can generate from business internet security, which is our managed security service, with sensors deployed all over the country. And in the opening presentation earlier this morning, Christy showed you a threat map, one of our front ends to that platform. And we added some feeds, some threat intel feeds. We are interested in ingesting everything from critical stack to APT nodes, Kiran Bandla's APT nodes, which is a terrific repository. I recommend you go ahead and use it. IIC suspicious domains, ThreatMiner and ThreatCrowd, Kaggle, VirusTotal, VXHaven. We even try to ingest Faraday reports from our pen tests. We run both internally and externally. We use SecRepo and Census and Rapid7 open data for vulnerability scans. And we put all this data together in this infrastructure, in this complex infrastructure that uses some algorithms to tell us in its current format actually to learn, to train our algorithms to detect, you know, your next big APT. We, of course, love the Elastic Stack. And we are using it. We love Kafka, we love Logstash, of course, Elastic and Kibana. It provides us with great flexibility. It provides us with great scalability. And we are actually thinking of, and doing it, we are writing our own filters, our own modules for it. This is a very quick overview of our architecture. We have everything from data collection to one end of the pipeline, to event viewing and custom dashboard and reporting. We do use the Elasticsearch servers for our ML algorithms and analytics algorithms. And we do offer some form of long-term storage in our Hadoop servers, just to trace back in case we missed something. But right there in your lower left side of the screen, we have some int things that are happening. And that's of course our open source intelligence and human intelligence and social media intelligence. We are ingesting tons of data in this pipeline and in other pipelines from the sources I've mentioned earlier in the previous slide. We are going about machine learning in two ways. On the supervised side, with supervised algorithms, that allows you to train your machines with training data, with data sets that teach the algorithms how to actually act upon a finding. And on the unsupervised side, where we have to rely on some more advanced methods of complexity reduction and clustering, in order to teach our machines what to do in case things happen. Right there in the middle, that's our sweet spot, because we are trying to use both techniques. In some cases, we are using supervised ML for things like malware detection, because it works out great. You just throw some sample data, some data sets at it, and it just churns that away. And we are using unsupervised machine learning for things that are more, subtle, like text mining and data mining from Twitter and forums and even dark web things. This is a very quick overview and representation of the algorithms as we are currently implementing them. You have your run-of-the-mill use cases for the supervised machine learning, and that is spam detection and malware ID. And of course, going above or below the baseline, our algorithms can help us detect some anomalies that we can act upon and investigate further. On the unsupervised side, we are using clustering and association rule learning. And as I mentioned before, dimensionality reduction in order to classify entities, in order to detect anomalies, and in order to explore to learn from available data. And one thing that this architecture allows us is to use the output of a chain of algorithms as an input for the other. If we go about entity classification from our unsupervised ML algorithms, we can use, in some cases, of course, that output in order to feed the input of our supervised ML algorithm. We are, of course, relying on text mining. This is not new. This has been done before. And you have great commercial solutions like Syntelix and Btext that are doing it for sentiment analysis. We are trying to read tweets and interpret them in the context that they've been written. For both alerting, because that is supposed to be the main reason you read tweets and you are on Twitter, just to know things like rapidly in your face. And in order to detect more subtle connections between some mentions, some verbs, some nouns, and some action that we are already seeing in our networks. It's a bit obfuscated for me to try to explain how this works, because we are actually in the process of building it. but our expected outcome, the expected results, we are actually looking forward to, to gain, is that our machine can get a bit of a contextual timeline about what has happened in our network relative to what people are talking about nowadays, today. And circling back to APTs. Well, I mentioned that there are maybe 6 or 7 stages that a complex threat uses in order to complete its mission. And 2 of them are establishing the foothold in your network, in your infrastructure, and lateral movement. And I've just picked the 2 because they are, of course, the most important, to show you how we are designing our pipeline, the pipeline in our X stack, to gain some new knowledge, gain some new information about the activity going on there. We are gathering logs, of course, and traffic dumps, if that's necessary. We are working with noise removal to exclude legitimate traffic. This is supervised machine learning for one part, so we actually taught our machines what is good traffic. We already label good traffic like business legitimate traffic that we know to a certain degree that it is secured. We are interrogating, of course, your run-of-the-mill IOC repositories, and we ingest data about known malware and known malware domains, because in establishing a foothold, the 2 main entry points in a network are phishing emails and social media. So we are keen on looking very, very, very in detail in that. And we are looking for anomalies, like large amounts of requests, single requests during the nighttime where most of our colleagues are not working, you know. Large DNS queries, why not? Because malware can be noisy. And of course, the output of this pipeline is an alert, a report maybe, and a very, very nice, you know, red bulb opening up in a Kibana dashboard. On lateral movement, well, this is actually a longer story, because we are using supervised machine learning to some extent here, and we actually got to the part where we had to train our algorithms to detect some kind of activity regarding the tools that most of the attackers might use to move laterally in a Microsoft domain, because most of our security domains are actually Microsoft, and we use Windows like most of your companies do for business, for business uses, of course. And you have your, you know, everybody knows them, your PSXec, your RDP, your Mimikatz with silver bullets and gold bullets, your PW Dumpex, your timestamp. These tools, they all create some form of footprint. They leave some form of crumbs, you know, be it in the Windows logs, be it in the application folder that they are running in. We got to the point that we analyze the logs and attribute and actually stitch together specific event IDs and specific attribute changes to some kind of activity that we decided that it can constitute a lateral movement. We literally just, you know, started PSXec, we watched the output, and we said, okay, I want to move from this to this, so I got to escalate the privileges like this, and if I was successful, if I was successful in doing that, I just collected the output, throw it to the ML algorithm, and let it decide for itself if my next try is going to be, was actually successful or not. We got to some pretty nice success rates, maybe in the 95th percentile by doing this. And we are kind of certain that if we continue to improve our algorithms and our data sets, the data sets that we're using to train the machines, we can go up to 99% in detecting, specifically detecting lateral movement with the use of some of the tools in my slide. And we have some output. It's a stack. And on top of the stack, you have Kibana. Kibana is pretty nice, right? You have your browser and you have your pie charts and everything. I mean, it's very management friendly. We can configure dashboards to show both live data and statistic data, analytics. You have some very nice alerting capabilities that can both alert operators and can interface via APIs with other machines, such as firewalls, if we want to go the full circle and automate detection and prevention. And of course, you have the reporting capabilities. This is what we are working with. This is actually what we, some of the things we wanted from the get-go when we began working on this tool, this kind of stack, this usage for an stack. And we are kind of pleased with it. And this brings us to our final question. I told you there are 3 questions, and this is the final one. Are we building yet another open source CM? No, we are not. We are very satisfied with what we have, as I'm sure you guys are, with your CMs. We are not looking into mitigation. We are not mostly looking into compliance. We don't want to build a machine that tells us if our network is, I don't know, some percent ISO 20027.1 compliant. We are not into that. We're just trying to teach our machines some new tricks. We are trying to go beyond just seeing the breadcrumbs, but we are trying to see the entire trail. And maybe this machine learning thing will help us. We had some references in the past with other, with some researchers in academia, especially building things like this. But unfortunately, they didn't have the required sheer volume of data to train their algorithms. I mean, the success of the rate of detection and the success of their stacks, of their machines, was limited by the lack of data, of real valuable data, not just statistical data, not dummy data, not generated traffic from a traffic generator. And we have that. And in closing, some nice stats. Again, from a Panimon survey conducted in the first half of this year. It says that companies using machine learning to detect threats can save up to $2.5 million in operating costs. Well, that's nice. And that 60% of them, in 60% of those companies, using such mechanisms can improve the productivity of their security people, because the security people actually have the time and to dedicate to other projects. And of course, in nearly 70% of cases, you get more speed. You get a quicker response time. Those 170 days that an average company needs to detect an APT actually gets down. And 60% of them, of the respondents, stated that machine learning identified their application security vulnerabilities. Well, this was it for my presentation. If you have any question, please, I'm here.
Thank you for the great presentation, Johan. We're going to take questions now. So as you know, please raise your hand and yeah, let's go for it.
Hi, thank you for the great presentation. I was wondering if this platform that you're developing, are you developing for a custom use, or do you plan to provide it as a service? And will it be dependent on your infrastructure that you have right now?
For now, we are just developing it internally. We are going to test it internally because some of the data we are going to ingest in the platform is internal data from our internal networks, not the client network, but our business offices networks. Mm-hmm. But okay. maybe, I don't know, in the future we can see if this is an option.
Okay. Thank you.
Thank you.
Cool. We have a question there in the back. Please.
We haven't. No, because our security guys do a great job. at securing our networks.
And another question was, are you using Mitre attack matrix in footprinting, or are you simulating specific attacks in order to learn to?
We are simulating specific attacks.
I was thinking. Thanks.
Okay, next one.
How does
We will get back to you.
how does your machine learning algorithm work with 0 days?
Well, you know, we didn't have a chance to work with a 0 day per se. We worked with some things that were already classified and labeled, that, you know, things that were 0 days a couple of days back. So we already knew the expected output. As I said before, we didn't get to actually catch something new. We just landed you know, spread our nets, but we didn't catch anything new. That's, you know, a honeypot's job. But with high-profile APTs that use 0 days, if that's your question, well, actually, the detecting rate, as I mentioned in a slide before, was somewhere around 95%.
One question from my side here. Okay. A bit tall I am. Are you using the machine learning capability within Elasticsearch, or are you using something custom built? And if you are using the capability within Elasticsearch, how are you handling labeling of non-numerical data?
We are actually using both the capabilities of Elasticsearch and some custom build solution from one of our partners. Well, about numeric data, I'm going to get back to you on that. I don't have the answer right now, but I'm definitely going to exchange some cards and I'm going to get back to you on that.
Okay, we have time for a few more questions, so please, okay, right over there. Please wait for the mic, so we can all hear you.
Okay, about machine learning, are you using statistical models or DNNs? That's one. And did you try to compute your F1 score? You know what a F1 score is.
Yeah, we are actually using some statistical models because we have to, you know, start from somewhere, and we are kind of new to this. Of course, it's something that we are working on. We are not at the point where we get to compute our own models, but maybe in time, in due time.
Okay, time for 2 more questions.
Hello, can you tell us what algorithms do you use for the supervised machine learning?
Well, that's the secret sauce.
I'm sure there are public ones. I'm sure that you use some public.
Actually, a partial disclosure is that we are working very close with some collaborators of ours that are helping us developing such algorithms. They are built for us from scratch.
Oh, there are custom ones,
yes,
not general ones.
Because as I've mentioned before, what we are trying to train our machines using our real life data.
Okay, thank you.
Last question.
Hello, thank you for the presentation. I wanted to ask you, when you built your machine learning models, do you use a specific technology such as Python or Scala, or do you have a specific software to build your models?
They are built in a specific custom software.
Okay, can you tell the name?
No.
Okay.
Okay.
I'm not trying to be secretive on purpose. It's just that this is the thing that we are actually developing. We are very invested in seeing this get from, you know, a hobby for a couple of guys in a innovation department back at Orange to something that we can rely on upon finding APTs. And I can maybe tell you more about it without going into the specific after this presentation.
Awesome. Thank you so much, Ioan. It was great having you on stage.
Thank you.